I was once again a little bit late in posting the lecture materials, but they are up there. So if you haven't gotten them, go ahead and get them. Okay, well, it's 3:41, so let's go ahead and get started. Hi, everybody. Hope everybody's doing well today. Today we are going to be talking about neural networks. This is kind of a really hot area in data science right now. So it's definitely something that we should touch on in an introduction to data science, but there is a lot, sorry about that. So there's a lot to say about this, but we're going to do, a little bit of a brief introduction to kind of get you started. So today in lecture, we'll talk about neural networks, and these can be used both for classification and regression. Most of the methods that we've looked at so far have been for one or the other, but these can be used for both. And in particular, we'll discuss perceptrons and multi-layer perceptrons, which are sort of the simplest neural network. And we'll look at how to do neural networks with scikit-learn and also a little bit on how to train a neural network. So some recommended readings, see chapters 9 and 10 from Hands-on Machine Learning with scikit-learn and TensorFlow, and also this resource on deep learning by Goodfellow, Bengio, and Corville. And there's a lot of tutorials out there on TensorFlow. TensorFlow we'll be talking about next time, but if you want to go ahead and check out some of the tutorials, there's a link right here. And also recommend watching some of the following videos from Welch Labs. And there's more specific links on these actually at the end of the lecture that I can point you to. Okay, and if you want to learn more, think about taking Math 7960, Topics and Statistics. I believe they cover some of the stuff in more detail. Okay, so let's get started with our imports. And the main new things that we're using today, let me highlight those right here, are from the sklearn.neural network library. We're going to be using MLP classifier and MLP regressor. So those are the two main new things that we're going to learn about today. Okay, so first of all, what are neural networks and what is deep learning? So artificial neural networks were originally motivated by the brain. The brain is composed of a bunch of neurons. How do neurons work? They fire these little signals at each other, and depending on what signals a neuron receives from other signals, it does some little it may fire or it may not fire. So this is kind of basically it's similar to the idea of neural networks in the sense that neural networks consist of basic computational units, and we call those basic computational units neurons. And there's information feeding into the neuron, and it does a little computation, and then information feeding out of the neuron. But the similarities with the brain basically stop there. So neural networks are not actually used to model the brain, and it's not actually how the brain works, but sort of, it's inspired this terminology because we have these little neurons. Okay, so they're generally used for supervised learning tasks. So there's, a response variable that we're trying to learn, such as classification and regression. You can use neural networks for unsupervised learning, like we were talking about last time, dimension reduction and reinforcement learning. So there are ways to do that with neural networks, but we won't talk about it here. And in the most classic cases, it's done for supervised learning. Okay, so after today, we're sort of collecting a toolkit of a toolkit of tools. That sounds great. And we have the following. So for regression problems where we have a quantitative variable that we're trying to predict, we've talked about linear regression. K&N, actually, we looked at more in the context of classification, but can also be used for regression. So that's one that extends to the regression context. Decision trees, neural networks, and for classification, we didn't really get time to talk about logistic regression, but that is one that you can use for classification. We talked about K&N, decision trees, SVM, and now we're adding neural networks. Okay, so we can add neural networks to our list, both for regression and classification. Okay, so large-scale neural networks are really at the core of deep learning, which has gained a lot of publicity in the last few years for its very impressive performance on a number of challenging machine learning tasks. So some examples are image classification, e.g. Google Images. So they're able to classify images, I mean, actually with really impressive tasks with an enormous amount of different categories and with very high accuracy. They're also used for speech recognition. So think Amazon's Alexa or Apple Siri, video recommendations like on Netflix, and even for beating the world champion at the game of Go. Okay, so really the applications of neural networks are everywhere, from imaging to speech to text to video, etc. Okay, so let's kind of get into the details of what these things are. These things are basically built from perceptrons. And so the simplest neural network is called the perceptron, and it was invented in the 50s by Frank Rosenblatt. And this perceptron is a binary classifier, okay, 0 or 1, and it is a function that maps a set of n features. So let's say I have my data, x, consisting of n features, x1 through xn. Here, this is all like a data point, you know, x1 is one feature, x2 is another feature. And I'm going to map this to a binary output, f of x, where I will say this function is going to be 1 if the inner product of w and x plus b is greater than 0 and 0 otherwise. Okay, does that kind of remind you of something that we've looked at before? Yeah, it kind of reminds you of support vector machines, right? It's like a linear classifier. You've got a line forming a decision boundary, and indeed, this looks a lot like support vector machines. So here the W is a vector of weights, and the B, right, when you're doing like precalculus, you would call that the intercept. In this context, it's often called the bias. So the weights and the bias. Okay, so it's often customary to represent this, this basic function called a perceptron with the following diagram, okay? Lots of diagrams in the neural network literature. So what do we have? We have our inputs. This is our input consisting of n features, x1, x2 through xn. And then we have our weights, w's. And so here in this diagram, this top weight, this W0, that's representing the bias. Okay, that's what was called B up here. So, but this is kind of a nice way to represent it all at once, where we just put the bias together with the weights and represent it in that way. Okay, so we have our input, we have our weights, and then this is all going to feed into some activation function, some nonlinear activation function. Okay, and the basic idea is like we did before. What we're going to do is we're going to train the network on data, on training data. And what that means is, like for support vector machines, we need to find the right W's and B's that are going to give us a good classifier. So in that sense, it's similar, like with support vector machines. We're looking for good values of these weights, W and B, that are going to give us a good classifier. And then we'll see how well the neural network performs on the test data set and use it to classify new points. Okay, so if you just have one perceptron, this is actually quite simple. This is just a linear discriminator, and that's very similar to support vector machines, what we've already done. But this is not really what we're talking about with neural networks and deep learning. It gets a whole lot more interesting when you put a bunch of these things together, when you start composing many of these perceptrons. Okay, and so that's what we're going to be thinking about doing, basically organizing a bunch of these things into a sequence of layers. And we're going to call this a multi-layer perceptron. Okay, so like the perceptron, a multi-layer perceptron, it also has, a set of values that are input. So these are features that we're going to input into the multi-layer perceptron. And we're trying to map these features. So we're going to map these features to some output or target Y, which we want to be close to a response variable. And in this diagram, we have a perceptron with 3 layers. Okay, so we have the input layer. This is what we're feeding into the neural network. We have a hidden layer, and then we have an output layer. Okay, so here we have 3 layers, an input layer, a middle layer, which is called the hidden layer, and an output layer. And this output layer should match so the dimensions here should match up with the Y that you're trying to approximate. So if you're trying to approximate a quantitative variable that was just one dimensional, you just have a single dimension to your output. If, on the other hand, you were doing something like image classification and you had the MNIST data set with 10 digits, then for the output, you would have a 10-dimensional output. You'd have a dimension for each class, telling you the probability of being in that class, okay? So the output dimension is kind of fixed by your data, right? By what you're trying to do. But the size of this hidden layer on the middle, it could be anything, right? You can make it big, you can make it small, you could put a bunch of them that you can really play with. Okay, so let's think about what we're actually doing here. So each layer in this diagram represents a function. So it's helpful to kind of take a look here. So what this first line is telling us is how we get the hidden layer from the input. So here, this little vector right here is the input. What happens? We take this little 3-dimensional vector, and then we are going to multiply it by a 4x3 matrix. And then we are going to add a 4-dimensional bias vector. Then we're going to apply a nonlinear function sigma, and that is going to give us the output. Okay, so this linear algebra right here is describing how we're going from this 3-dimensional input layer to this 4-dimensional hidden layer, right? We take a 3-dimensional vector, we multiply it by a 4x3 matrix, add a 4-dimensional bias, and that's what we're doing here. Okay. Right, and so in the notation that I was using before, this is the W, right? These are the weights that we want to figure out what are good choices of these weights and bias. All right, and then finally, to go from the hidden layer to the output layer, what are we doing? We're mapping a 4-dimensional thing to a 2-dimensional thing. So what size matrix do you need for that? You would need 4 by 2, right? So to map a 4-dimensional thing to a 2-dimensional thing, you would need a 4 by 2 matrix. And so that's what you're doing here. You're going to have some matrix, some set of weights. You take your 4-dimensional vector, your hidden, which is the vector from your hidden layer, multiply it by that matrix and add a 2-dimensional bias. And then apply a nonlinear activation function. Okay, so this sigma, all right, so basically think of this as a composition of what do you do? This is not many layers here, but you could have a bunch of hidden layers, and it's basically a composition. You apply a linear function, then you apply a nonlinear function. Apply a linear function, and then a nonlinear function. Linear, nonlinear, so you just have this cascade, if you will, of linear and nonlinear functions. The nonlinear function is generally applied just entry-wise, right? So all I would do is to apply the nonlinear function to this vector, I just apply it to each entry. Okay, so if you've never seen this before, it can be a lot to absorb, but actually the basic building blocks are actually fairly simple. What gets complicated is when we use a lot of layers. Okay, and so, right, so like I said, the sigma is the activation function, which we'll discuss in more detail in a bit, and an additional function, oftentimes the output layer gets its own special activation function that's different from what you're doing in the hidden layers. And if you're doing a classification problem, the activation function for that last layer, for the output layer, is generally going to be a softmax function. And basically what that does is it takes numbers, which could be in any range, from whatever, -20 to 100, and it scales them to give you probabilities. So the softmax layer would take, whatever the output is, and then map it to a probability in the interval 0, 1. Yeah.
Sorry, so an activation function, is it a scalar or?
It's not a scalar, it's a function.
Okay.
Yeah. So we'll talk about some possibilities in a bit. ReLU, if you've seen that before, is the most common one, or think like hyperbolic tangent, or just literally some function where you plug in an input, get an output. Yeah. Other questions? Okay, so please interrupt me with questions because I think this can be a little confusing when you're first saying it, and your questions will help me explain it better. So, okay, so let's see. So basically, what we want to do when we train the network, it means we want to find the best possible weights for this problem. So that means the best matrix here and here, and the best biases here and here. Often we just call all that the weights. All of these scalars appearing in these matrices and vectors, these A's and these B's, we just call them all the weights. And we want to figure out what the best values of those parameters are to give us the best output that's the best match for our training data. But you notice this is a really small example. We don't have a whole lot of neurons here. We've got one layer, one hidden layer of 4 neurons. And already we're looking at, we've got this 4 by 3 matrix and this 2 by 4 matrix and these vectors. We already have 26 parameters. And that's a lot. I mean, it's not a lot compared to the number of parameters for neural networks, but it's a lot compared to the number of parameters that we've been messing with in the other methods that we've looked at, right? Like support vector machines, you know, we might have been playing with 2 or 3 parameters. Here we're going to be looking at a bunch of parameters. Okay. So, so the way in which we put the neurons together, the way in which we organize this network is referred to as the network architecture. And the perceptron and multi-layer perceptron are 2 examples, which are kind of like the simplest examples. There are a whole lot of other ones. This is just giving you a little peek at some of the many, many different architectures that are out there. What we're going to be focusing on here are what are called feed-forward neural networks. Feed-forward neural networks basically take an input and it flows forward through the network. But it never, in some networks, you might have like, you have an input and it starts flowing forward and then it kind of loops back around and gets input again. That can get more complicated. Those are called like recurrent neural networks. And we're not going to be dealing with those. So the kind of the basic one we're going to be talking about is feed-forward neural networks, where you put in, you put an input in and it just flows through the network and gives you an output. Okay, so think, right, yellow, I have my input cells, I have my hidden layer cells, and I have my output here in red. So recurrent neural networks sort of feed in. You'll notice like after you get the output, it like feeds back in to the hidden layers. So those are a bit more complicated, but they're really useful for data, which is when you have data that consists of like a temporal sequence or even like a sequence of text. So anything that has this like sequence structure to it, that's a useful architecture for. An autoencoder is a neural network that's used for dimension reduction. Yeah, you got a question?
I do. I think it's just like a clarification. So like neural network basically just means a sequence of functions and like how they're using like inputs and outputs to like reevaluate, I guess.
Yeah, so it's a little confusing because it can mean a lot of different things. You know, I would say in its simplest form, have this picture in mind, right? This is like the simplest way to think about a neural network, but there's a lot of variations, some of which don't even have a response function. So that's like quite different, right, than this setup here. But what they do have in common is basically this like cascade of linear functions composed with nonlinear functions and using a lot of cells. Yeah, good question. Yeah, so like in the autoencoder neural network, there your goal is really like dimension reduction. So you take some input and you like squeeze it into a narrower layer in the middle of your network and then unsqueeze it. And then whatever you get here in this like squeezed version should be good features for dimension reduction. Yeah.
So by linear, like one versus like multiple to one.
No. So you can have a nonlinear function that's still one-to-one. For example, like something like that, you know, like an S or yeah, think like x cubed, right? So you can definitely have one-to-one that's not linear. So by linear, I mean like literally linear. Yeah, like a flat, straight thing. Okay. And then convolutional neural networks are used a lot in image processing. Those are quite popular in that application. So, okay, so a lot that we can do here. But maybe let's not get too far. Let's focus on, first of all, the feed-forward neural networks and get an idea of what they do. Oh, look, here they have support vector machines listed as a kind of neural network, which is interesting. Okay, so great question. What actually makes it a neural network when all of these things look so different? But the most important thing about all of these is that there's an input layer, which we usually draw on the left, and there's an output layer, which you usually draw on the right, and then we have middle layers, which we call hidden layers. And when we say a deep neural network, what we mean is we mean a neural network that has many hidden layers, okay? So not just 1, 2, or 3, but usually like 100 or something like that. Okay, so for example, neural networks have been super useful on imaging tasks. So this data set in particular, it's called ImageNet, has been a test data set for visual object recognition. And this data set consists of 14 million images, which have been hand annotated. That must have been a fun task. Hopefully some poor students were adequately compensated for that. And there are approximately 20,000 categories, such as balloon, strawberry, cat, dog, etc. And so they run like a competition every year for different methods to compete on how well they can do with this classification task. I think for the competition, they don't use all 20,000 categories. I think maybe they use 1,000 or something like that, but still a lot. And so what you notice, this little graphic is just showing how the performance in this competition evolved over the years and how that kind of huge increase in performance happened with the onset of neural networks. So notice how most of these methods here were not doing so well. But the first year that a team tried a neural network approach, they did really well. And then in subsequent years, as more people focused more on these neural network methods, they got like increasingly more impressive performance on this really challenging data set, till finally almost all the teams were getting less than 5% wrong, and mainly with neural network-based methods. Okay, and in 2017, the winning solution used a neural network with 154 layers and about 10 to the 8th parameters. So think about that for a second. 10 to the 8th parameters that they had to train for that. It's crazy. Yeah. Okay, so let's see how we can actually implement these things in scikit-learn. It has a nice little library for this, but let me sort of say it's not really intended for large-scale applications, but it's really great when you're first learning about these things and what the important parts are. It's a great way to play around with it, but it doesn't offer GPU support, and it also doesn't have as much flexibility if you really want to change things, but it's a great place to get started. Okay, and there's basically a few different functions in this in scikit-learn. So that you have your perceptron, and you've got your multi-layer perceptron or MLP classifier and your multi-layer perceptron regressor. And so these last two are what we're going to be looking at because we're interested not in a single perceptron, but we want a multi-layer perceptron, that is a neural network, and in the context both of classification and regression. Okay, so let's start off with our moons data set, which we have done a few times before. So we'll generate some data with our make moons function. And then take a look here. I've got my red points and my blue points kind of in this curvy shape. Okay, so let's train a neural network to do this classification problem. So this is the basic syntax that we would use. So first of all, we're specifying a model like we've done in the past. We're going to use an MLP classifier. We have to tell it, at least there might be a default for this, but in general, you want to specify how many hidden layers you want to use and the size of the hidden layers. So here it says 3, 3, 3. So it's saying I'm going to do 3 hidden layers, and each hidden layer is going to have 3 neurons in it. So this is 3 layers of 3 neurons each, right? If you had like 3, 5, 3, it would be 3 layers of 3 neurons, 5 neurons, 3 neurons. And then you tell it the maximum number of iterations you want it to run. That's kind of similar to a parameter that we had for k-means. We'll get into what this alpha is in a little bit. And basically, to train this model, you have to solve an optimization problem. And you have some different options on how to solve that optimization problem. So you specify your solver, and you can specify a random state for reproducibility. Okay, so well, let's not get too far into the weeds on that, but let's see what happens when we do this. So we have a loss function. I'll go into exactly what that is in a little bit, but remember, what's it trying to do? It's trying to find the best weights, the best W's and B's to make the best prediction. And so it's measuring how well the W's and B's that it's using are matching up with the training data, and it's gradually able to find, to reduce the loss to find better and better weights. Okay. Until finally it converges. Okay, so let's take a look at what it actually did. So once again, we'll just plot the data and then take a mesh of points and apply this model.predict function, right? We've specified what the model is, and then we fit the model, and now we can call this model.predict to actually evaluate that MLP classifier on new points. And then we can plot the results using our contour plots like we've done in the past. And so we kind of see this is what the MLP classifier is doing. It's splitting it up into a red region and a blue region. It looks like it's working pretty well on this data. Okay, and so let's dive in a little deeper though into what it's actually doing here when it does this. So it ran for 45 iterations and finally decreased the loss to 0.1. And one thing you can do is you can print, I think this is helpful when you're first getting started to get the picture clear in your head, print the model coefficients and their shapes to see what it's doing. So the model coefficient shapes are 2 by 3, and then 3 by 3, 3 by 3, and then 3 by 1. Let me see if I can. I'm going to try to draw this. Might not go great, but I'm going to try it. Okay. All right, so what's going on here? What is the dimension of the data? What's the input dimension for the moons? Yeah, so just 2-dimensional, exactly. So we've got, right, we have an X coordinate and a Y coordinate for each data point. So this is just 2-dimensional data. So we would represent that in our input layer with these 2 little dots or neurons. And then what we specified in the architecture was that we were going to use 3 layers of 3 neurons each, right? So what it's doing, it's making a network that looks like this. Okay. And then finally, it's going to do its output layer. And for a binary classification problem like this one, which is just 0, 1, that output is just going to be a single thing, which is like the probability of being a 1. Okay, so this is kind of what it's looking like here. And then let me see. Can I draw? Yes, I can. And so this is kind of fun because it's got the arrows on it, so you can really see how it's feeding in here. Okay, right. So all of these feed into all of these, and then, right. So you kind of notice why it's called a network, right? Because all of this stuff is connected and feeding in. Okay, I'm not going to draw all these, don't worry, but you get the idea, right? Same thing going on here. And finally, everything feeding into this output layer. Okay, so that's the architecture that we have here. 2-dimensional input, 3 hidden layers, each with 3 neurons, and a 1-dimensional output. And so you can see how that matches up here with the model coefficients. So if you're, first of all, you have, and notice you have model coefficients and you have model intercepts, and these are stored differently. But for our model coefficients, we have a 2x3 matrix that maps us from here to here. Then we have a 3x3 matrix, which maps us from here to here, another 3x3 matrix mapping us from here to here. And then finally, we have this 3x1 matrix or vector mapping us from here to here. And we also have the intercepts or the biases associated with each of those as well. Yeah.
So it's only one matrix multiplication in each of the features. It's not like there's a separate 3x3 to get.
That's correct. Yeah, that's correct. So think of this as like a vector where each entry of the vector is like a value of the neuron. And indeed, to go here, you're multiplying by 1 matrix. Yes. There are more complicated setups where you have different channels, and like different matrices, but yes, 1 matrix for each of these, layers. Yes. Yeah, was that no, you didn't have a question. I have a question in the chat, hold on. Oh, I have an answer in the chat. Thank you. Okay, so hopefully that, just kind of seeing exactly what these things are helps it click a little bit. Yeah, 1 matrix to go in between each of these layers. And then you'll notice if you output the model parameters, you get a lot. Okay, so there's a lot going on. There's an activation function, there's an alpha, there's a batch size. We're going to talk about some of these. We're not going to talk about all of them, but we will talk about the activation function. We'll talk about the alpha. We'll talk about the solver and a few other things. Okay, so I guess I can clear this picture. I'm just so proud of my little drawing. Okay. Okay. Okay, so as you can see, there are a lot more function parameters for MLP classifier than for the other methods that we've looked at. And changing them can make a big difference, okay? So it's not like they're unimportant parameters. Let's take a look at a couple of the most important ones, though. Okay, so first of all, let's look at some parameters related to the architecture. You have your hidden layer sizes, right? So that's very important. So when we did this example, what did we say? We said hidden layer sizes, 333. That's what we said. But we could say whatever. We can play with that. There is a default for that, which is 100. Right, sorry. The default, yeah, so I guess I'm trying to figure out if that's the default for the number of layers or the number of neurons in the layers. Actually, I'm not 100% sure, but when you specify the hidden layer sizes, the number, you're telling it basically the size of each hidden layer, and so the number that you have there will specify how many numbers you have, specifies how many layers you have, and what the number is specifies how many neurons in each layer. Okay, so then you choose your activation function. So some of the options for this are the identity function. You probably don't want to pick that because that doesn't do anything. So if you pick the identity function, the sigma doesn't do anything. And essentially you just have a composition of linear functions, which is another linear function. So you're just doing regression, right? So probably don't want to do that. Not sure why it's an option, but it's there. But your other options are logistic, hyperbolic tangent, and ReLU, which is by far the most popular choice and tends to work very well. We'll take a look at the plots of these so you can get a better idea of what it is. The ReLU function is defined as sigma x is just the maximum of 0 and x. It's kind of interesting. It's like almost linear, but it's not. It's linear, in the positive domain, and it's just 0 in the negative domain. Okay, and then you have this alpha parameter, which has to do with the loss function, which we'll talk about in a little bit. And then all of these parameters relate to solving the optimization problem. So you have different solvers that you can choose from. LBFGS is in the family of quasi-Newton methods. You have stochastic gradient descent. You have ATOM, which is a variation on stochastic gradient descent. And you can specify a maximum number of iterations. If you don't want it to go on forever and ever and ever, you might, tell it stop after whatever, 500 iterations or whatever you think is reasonable. And if you want reproducible results, which is good for your projects, right? So good to specify a random state that's going to give you the exact same output every time you run your code. Okay, the tolerance also has to do with the optimization, and it basically just says, it's trying to minimize this loss function. And so at some point, it'll get to a point where it's not able to make it very much smaller by going in any direction. And it'll say, I think I've converged, but you can kind of control when that happens with the tolerance. So if you have like a really low tolerance, like 0.0000001, then even if there's just like a tiny improvement that you get by moving a little bit, you'll go ahead and do that instead of saying, I'm close enough to the minimum. Okay, and then if you want to see all the output, you can choose this verbose option. Okay, so let's take a look at the activation function, just so you can see what it looks like. So here's some of the different options. Like I said, there was logistic, ReLU. This is just a derivative function for the purposes of plotting things. Let's take a look at these plots. Okay, so like I said, the most popular one is ReLU, which is just 0 for negative numbers. And then it's just the line y equals x for positive numbers. So it's almost, it kind of looks linear, but it's not. This corner is quite important. And then these other options, the logistic function is here in green. It's kind of an S-shaped curve. And the hyperbolic tangent is also an S-shaped curve, just over a different range. And so it's interesting to think about the derivatives of these activation functions. If you look at their derivatives, you get the following plot. So what's the derivative of y equals x? Guys remember that? 1, right? So that's here, right? The derivative of y equals x is 1. The derivative of 0 is 0. So the derivative of the ReLU function is just like the step function. So it's 0 over here, and it's 1 over here, and you've got like this discontinuity in the derivative here. On the other hand, the derivatives for the logistic function and the hyperbolic tangent function are more bell-shaped, almost like a Gaussian. Okay, so one reason that ReLU is really useful for deep learning and neural networks is that no matter how large the input, right, x could be 100, say, the derivative is still going to be 1. On the other hand, if you think about what's happening with some of these other activation functions, as the input gets really large, notice how these bells, what are they doing? Well, they're decaying. They're converging to 0. So when x is really large, like 100 or 1,000, the derivative is going to be really, really small. And that's going to make it more difficult to train the neural network than if you have a derivative that does not get really small. So that's a phenomenon known as like the vanishing gradient phenomenon, and a reason why ReLU is preferred. Okay. All right, so, okay, so a few things I think have been a little mysterious, such as what are we optimizing when we're doing this? So we're going to go into that, but let me take a little break there for any questions before we go into what exactly we're optimizing. Okay. All right. Should we take our break? You guys want 5 minutes? Let's do 5 minutes. And we'll come back at 4:33. We can do this. It still looks like we have a lot left, but it's some really long output cells. All right, let's get started again. Okay, so now we're going to talk a little bit about training a neural network. So what are we actually doing here? Well, remember I said we're trying to find the best weights, right? The best matrices to use to get the best classifier. And so to do that, one defines a loss function. So we have a loss function where we think about essentially evaluating how good a job are the W's that we're currently using, how good are they doing? So think whatever weights you have used to define your neural network, they are going to define your prediction, y hat, because you feed in an input, it uses those W's to compute an output, and that defines your y hat. And basically, you want to think about how well the y's, the actual response values you have in your training data, and the y hats, the outputs of the neural network are matching up. So, the loss essentially tells you how close y and y hat are. But remember, y hat here is completely a function of w, right? You change the weights, you change the output. So really, think of this function as a function. Think of the y's as fixed by your training data, and think of this loss as a function of w, of the weights. Okay, so what is it exactly? Well, first, we have some data fitting term here, where we're essentially looking at what are the y hats predicted by the neural network, how closely do they match up with y? We evaluate with some function f, which measures error. So this could just be like the L2 error in the context of regression, or it could be cross entropy in the context of classification. But basically, this term is a data fitting term, which is getting the y hats to match up closely with the y's. But it's possible to achieve that on the training data, sometimes by doing really crazy things with the weights, by like taking them really, really large. And that's usually not desirable for generalizability. So we have this regularization term, which prevents us from blowing up the weights, right? Because we're trying to minimize this loss function. So we can't make the weights too big or this thing will blow up. And so your choice of alpha is essentially going to balance, these two pieces to the loss function, which is your data fit part and your regularization part. Okay, so the y's are the true labels, the y hats are the predicted labels predicted by the neural network. W is all of our parameters, right? Both the matrices, the weights, and the biases. Everything is being called W here. And F is whatever function we're using to assess the fit. Okay, so, well, how do we start one of these things, right? We want to find the best weights. In general, we usually just initialize things randomly. So we might just initialize all of these matrices to be a Gaussian or some other random variable. So we start off with the random initial weights, and then the loss function is minimized by repeatedly updating these weights. And the details will depend on the method that we're using. So some of the options that we mentioned was stochastic gradient descent, ADAM, LBFGS. But really what most of these methods have in common is that they're gradient based, and they're basically doing gradient descent. Have you guys come across gradient descent in any of your other classes? So some of you have, some of you haven't. Okay, what is the idea of gradient descent? Gradient descent is when you're trying to either minimize or maximize a function. Let's say we're trying to minimize, actually I can draw this. Let's say we're trying to minimize a function, okay? And so let's say I am right here, and I can evaluate, I know where I am, and I can also compute the gradient And so the gradient in this case points in the direction of greatest change, which would be up the hill. And the negative gradient is going to point in the direction of greatest decrease, which would be down the hill. So the idea of gradient descent methods is you've got a function you're trying to minimize wherever you are, you compute the gradient, and then you take a little step in the direction of the negative gradient. So I would step down here, and then I would compute my gradient again, and then I would step down here until finally, I get to the bottom of this hill, and here my gradient is 0, right? Because I'm at the bottom of the hill. And so then I wouldn't go anywhere, I'd just stay there. So that's basically the idea of gradient descent methods. Okay, so let me clear that. So in this context, what we are trying to minimize is this loss function right here. And we are trying to minimize it with respect to W. So we will take the gradient. So we think of W as the variable here, right? So we take the gradient with respect to W of the loss. And then we're going to update our weights by taking a little step in the direction of the negative gradient. So if we are currently have the weights W, we're going to update these weights by W minus some step size epsilon times the gradient of the loss function with respect to W. And then the algorithm will stop when it's reached a preset maximum number of iterations, or when it converges, like when it gets to the bottom of the hill, right? If it gets there, it'll stop, or it may stop if you've set some max iteration. Okay, so how do you actually compute the gradient of W? Actually, it turns out that in some ways, in some sense, it's not hard to do. We know sigma, we know what activation function we've used, and we just have a bunch of these linear functions. So you can actually compute the gradient of the loss with respect to W with the chain rule. It just gets super long and nasty and messy if you have a very deep network with a lot of layers. And so there's like a clever way that you can organize these calculations called back propagation so that you can do them quickly and efficiently. But really it's just sort of a clever implementation of the chain rule when you do back propagation to compute the gradient for training a neural network. Okay, so we can just take a look here at the performance. So so when we're minimizing this loss function, there's different solvers that we can use. We can use stochastic gradient descent. We can use Atom. We can use this LBFGS. We're not really going to go into all the differences. You can check them out if you're interested. But let's just take a look here at this code to sort of see what the performance is as we vary some of these different things. One thing that one kind of semi-important thing, maybe I'll point out here, is a parameter called the learning rate. What is that learning rate? Well, this learning rate, it has to do with the epsilon here when we're doing gradient descent. So if you have a small learning rate, you're going to take tiny little steps, right, in the direction of the negative gradient. If you have a large learning rate, you're going to take big steps. Now, what do you think is better? Big steps or little steps? You say little steps? Anyone want to argue for big steps?
Big steps if you don't have a long time.
Yeah. I mean, you want to take big steps if you can get away with it because it'll get there faster. But the risk is that, you overstep where you're trying to go. And so if your steps are too big, you might just hop over, your minimum altogether. So definitely there's like a strategy here, can be tricky. Taking little steps is safer, but it could take much longer to converge. So what a lot of people do is start off with big steps because they kind of start off assuming you're really far away from where you want to be. And then as the iterations increase, they start making the steps smaller and smaller. So that's another kind of strategy. So here, the learning rate, you can see, you can set it to be constant. So that's going to keep that epsilon fixed at some constant value. Or you can set it to have an inverse scaling where you start off taking big steps and then you start taking small steps the more time goes on. And that's kind of handy, this inverse scaling. Okay, so let's take a look at how some of these methods perform. I'm just going to skip through this and we can look at the plots because that's really kind of what we care about. So here we have a couple of different methods that we're comparing. Stochastic gradient descent with a constant learning rate, stochastic gradient descent with momentum, and then we have this inverse scaling learning rate, inverse scaling with momentum, atom. You may notice this, this method, atom, oh, and this is on 4 different data sets: iris data set, digits data set, circles data set, and moons data set. The atom has pretty impressive performance across all of these data sets. Atom is doing really well, right? This black line tends to be at the bottom of these methods, as is this stochastic gradient descent with Neisterov's momentum. That seems to be doing well too. Okay. So just to kind of summarize here, there's some recommendations on this page, so you may want to check that out. And so they sort of observed empirically that the LBFGS converges faster and better on small data sets, but if you have larger data sets, atom works very well and is very robust, or stochastic gradient descent with Neisterov's momentum. So anyway, there's so much on this. So a lot of people, there's a lot of research and a lot of work on the best optimization methods for that. So just know that it's out there. But, you know, atom is a good default if you don't know what to use. Yeah.
What's the y-axis on this? Is that just the data?
Yeah, that's the error. So this is great question. Sorry, I didn't specify.
And the x is the iterations.
Yes. So we're looking here at, you know, so this is kind of telling us like how long it's taking to converge and also how good we're doing at the end of the day once we converge. Yeah. So that's a good point. So you're looking both for like these methods to get a small error, but also you want them to get there quickly. So you want curves that go down rapidly, really fast in the beginning, because that means they're converging quickly and they're getting small error. And I've got a question. Oh, so we've got a good question here. Are iterations synonymous with epochs? That's a great question. I don't think so. I would have to look up the definition of epochs, but I kind of think that's more of like a longer period than a single iteration. I can look at that for next time to have a better answer on what is meant by epoch. Other questions? Okay, so maybe let's try this on another data set. So this is the breast cancer data set, which is one of the built-in data sets. So that's nice. So first we can just load this. And then we can print the keys here just to get a sense of what is included in this data set. When we print the keys, we see the following: data, that's where our features are stored; target, that's where our response is stored; frame, target name, description, feature name, file name. And so then if we print the description, that's helpful because it gives us a sense of what this data set is. So in printing the description, we see this data set consists of 569 data points. Each data point has 30 numeric attributes. This is, so like I said, this is a breast cancer data set. So these are the features here: radius, texture, perimeter, area, etc. The data set it consisted of like images of tumors. So each data point is like an image of a tumor, but then inside the image, you have a bunch of different cells that are appearing in the image. For each cell, for each cell in the image, they measure the radius, the texture, the perimeter, the area, etc. But then what they actually record are the mean and the standard deviation and the maximum of those numbers over all cells in a single image. And then so they can associate, a value of that for each image. So that's kind of what's being done. But at the end of the day, we have these about 570 images of tumors. Each has 30 features associated with it. Okay, so let's, and then the target, right, the response variable is just whether the tumor was malignant or benign. So that's stored in there. And that's what we're trying to predict from all of these, basically from the image and the features that we extract from the image. We want to predict if the tumor is malignant or benign. And so we can specify that we're going to use a multi-layer perceptron classifier. Here, we're doing a hidden layer, 3 hidden layers, each with 30 neurons. And we're going to fit this classifier using our training data. And so I should say, right, remember that when we after we loaded this data, we used our train test split function to split it into training and test. That's generally what we're going to be doing in all of these examples: loading the data, splitting it into training and test data. Then we'll train on the training and see how it does on the test. Okay, so fit it on the training, and then we will predict it on the test and look at a little confusion matrix here of how well it's doing on the test data. And it's doing pretty well. Right, it's getting like 7 of those. Looks like 7 are misclassified. But yeah, doing pretty good. Notice it kind of, I'm trying to see if, oh yeah, right. So because I fixed the random state, this is staying the same. But notice if I hadn't done that, right, if I had not fixed my random state, then, so if I take this out, then probably, right now it's going to vary run to run a little bit. So this random state is giving me fixed output. Okay, so all of the examples that we've tried so far have been binary classification, right? Red point, blue point, or malignant, benign. So let's take a look at the IMNIS data set, which consists of 10 classes. And so here we'll take a look at a larger version of the data set than we've actually used in the past. This version has 70,000 data points, and each consists of 28 by 28 pixel images and a label corresponding to which digit is, ranging from 0 to 9. Okay, and so if you're following along, I actually downloaded that data has been downloaded from this website here, and I have added it to the lecture repository folder, but it's very large, so I zipped it. So if you are following along, you just need to unzip this file, this IMNIS original.mat file that's in the lecture folder. Just unzip that before you run this code cell. Okay, so we're gonna, first of all, load the data, which is just being stored inside the folder, and then we can take a look here. at the keys for this data set. And what do we see here? We see we've got one called data and we've got one called label. Okay, so let's go ahead and train our MLP classifier. So now we're just going to use 2 hidden layers, each with 100 neurons. And let's say 400 iterations. Right, this alpha, remember, is balancing the data fit term with the regularization term. And let's use Atom and see what we get. So this one will take a little longer than what we've done before. Here I think we're using most of the data. We're using 60,000 data points. So this is a big data set. So notice, this is gonna take a little while. And we're using 100 neurons in each layer. But it's not gonna take too long, but it's gonna take like, I don't know, a minute. Okay, so while that's running, well, we can go up and take a look at what happens. Actually, it's almost done. We'll just wait for it. There we go. Okay, so you can see the loss function decreasing until finally it converges because it can't really make the loss any smaller regardless of what direction it steps. And then the score on the training data is 1. That's good, right? 1 is like 100%. We did really good. And then if we evaluate the performance on the test data set, here is the confusion matrix comparing the labels in the test data set with the labels predicted by the neural network. And it's doing really well. Remember, all the diagonal entries are correct. And so that's about 98% correct, which is, I don't know if you remember the performance that we got previously with the other methods. It was not 98%. It was much lower. Okay. And then this is just to kind of clarify what's happening here. So the dimension of the input, they're 28 by 28 pixel images, which you vectorize. And so the input here is 784 dimensional vector. Okay, and then what does it do? We've got these 3 layers, each with 100 neurons. So we're going to have a matrix that's 784 by 100, and then one that's 100 by 100, and then another one that's 100 by 100, and then we're going to have one that is 100 by 10 to map to that final output. And now here, the output is 10. I found this a little confusing, honestly, because for binary classification, the output is one-dimensional, right? You have 2 classes, but it's a one-dimensional output. But for K classes, for multi-class, it's K-dimensional, if that makes sense. So it's actually doing something slightly different if it's binary classification or if it's multi-class classification. It's like slightly different. For multi-class, it'll output a dimension, which is the number of classes. For binary, even though there's 2 classes, it just outputs 1 dimension, but it's using a different activation function in that last layer too. For the binary classification, it's using a logistic activation function in the output layer. And in this case, it's using a softmax. Okay. So if you're interested in what it's doing, you can ask it to print the output activation function. And here you see it's using a softmax. Okay, and so if we have time, I'm going to have you guys go back and see if you can improve upon that 98% by adjusting the some of the parameters, right? So the architecture or the parameters and the optimization. Okay, but we might not have time. Indeed, I don't think we will. So let's see, what did I still want to talk about? Wanted to talk about regression. And maybe I'll just talk about that next time so we're not rushed. I could probably get through it in 3 minutes, but any questions that you guys have? Is this like clicking? Is it really confusing? Is it?
Like the math and logic behind it's kind of, but I think like following your code, like on homework or something, I can, probably tune it, play around with it a little bit to get started.
Yeah. Yeah. So just try to make sure, try to have that picture in your head, right? About what is it actually doing when you input a vector? What's the process that it goes through? Basically it's just like matrix multiplication, nonlinear function, matrix multiplication, nonlinear function. And they're just doing that, over and over and over again to finally output something. Okay. Well, why don't we go ahead and stop there? We really got through most of this. Next time, because we're going to continue our discussion of neural networks next time. Next time, I'm going to be talking about TensorFlow, which is another implementation for neural networks in Python. And and it's better for large scale applications. So if you really want to do large scale applications, it's good to use that. And then we'll also talk about the MLP regressor function. I'll go over that next time, but there's really not a whole lot to say because it's so similar. It's just like the MLP classifier. It's just, the output is like a quantitative variable, but basically all of the inputs and all of the things that you're sort of doing to design the network are very, very similar. So, so we'll go through this at the beginning of next class, but it will be very similar to what we've done. Okay. Thanks, everybody. Have a great evening.